Thank you to Brilliant.org for sponsoring today's video. More on them in a bit. The film critic Roger Ebert said a great movie was one that you could return to year after year, and it said something different to you each time. Similarly, I think a great math problem is one that you can return to over time and see something different in. For today's video, I have one of those problems for me. I first saw this probably 5 or 6 years ago, and I would say I returned to it every 1 or 2 years, and I'm always seeing something new in it. Honestly, I love finding new problems like this, so if you have a math problem that you have returned to over and over again, please put it in the comments down below. I love solving new math problems, and I'd love to have some of these deep problems that I can return to year after year. Let's get into it. For some x, y, and z, let's imagine that we know x plus y plus z equals 1, and then their squares, x squared plus y squared plus z squared equals 2. Their cubes, x cubed plus y cubed plus z cubed equals 3. What do we think we can say about their fourth powers? X to the fourth plus y to the fourth plus z to the fourth. Naively, you might say, well, maybe it's 4, right? Maybe this pattern continues. But spoiler alert, I can tell you it's not 4. To walk through how I solve this problem, I want to think about certain principles for problem solving. And the first one is the best one. Solve the easier problem first. In this particular case, rather than consider the three-dimensional problem, the XYZ problem right off the bat, let's think about a two-dimensional analog. Let's imagine that we had some x plus y, which was equal to 1. The squares, x squared plus y squared, is equal to 2. What can we say about the cubes, x cubed plus y cubed? Again, very naively, we might say, well, maybe it's 3. And again, we'll find that's not actually the case. It's not 3 here. Now, one thing that's interesting about this easier problem is it's just a system of equations. Specifically, it's a 2x2 system. It's 2 equations in 2 variables, and usually in that situation, we have enough information. In this particular case, though, because one of the equations is being squared, it might feel like we have less information than we need. So in fact, our second principle here is you often have more information than you think you do. Let me show you what I mean. A typical way to approach this would be to do something like, well, if we know that x plus y is equal to 1, let's square both sides of this equation and see what else that shows us. In this particular case, that means we need to be able to take x plus y and multiply it by itself. Now, my preferred method for that is what I call the box method, or the area model for multiplication. But you may prefer FOIL, double distribution. It really doesn't matter. The main thing we need to do here is just multiply out x plus y times itself. X times x is x squared. X times y is xy. Again, x times y for this lower left-hand box is xy. And then y times y is y squared. Adding together our like terms, we can say that gives us x squared plus 2xy plus y squared on the left-hand side. On the right-hand side, 1 squared is equal to 1, and so we can say that this quantity stays 1. But that's interesting. This is what's going to get us some new information because we actually already knew what x squared plus y squared was equal to. X squared plus y squared is supposed to be 2. And so essentially we can do some substitution now. That x squared and y squared can be replaced with what it's equal to, 2, and then the rest of the equation stays there, plus 2xy on the left and 1 on the right. This means that this new term that popped up when we squared both sides of that equation, we can solve for that. We know the value of x times y. If we subtract by 2 on both sides here, we get 2xy is equal to -1, and then if we divide by 2, we get what appears to be a new piece of information. It's not really new. We had the information before, it just wasn't in this format. Let's put that over here along with the other information we have. X times y is equal to -1/2. In fact, let's also go ahead and label some of this information so it's easier to keep track of. The two things we were given initially, x plus y equals 1 and x squared plus y squared equals 2, we'll call A and B. The thing that we're looking for, we'll label C. And then this piece of information we just figured out, xy equals -1/2, we'll call D. From here, I'm going to do a similar move, although instead of multiplying that first equation, the left-hand side by itself, I'm actually going to multiply A times B. I'm going to combine those first two pieces of information. On the left-hand side, that's going to be x plus y times x squared plus y squared, and on the right-hand side, that's going to be 1 times 2, these values over here. Again, I'm going to use something like box method to multiply out this left-hand side, and I'm going to get x to the third power this time. X times x squared is x to the third, plus x squared y, plus xy squared plus y to the third. And here's why I'm very happy about this. If I write down the product of those two binomials, I get x cubed and y cubed, and of course, that's the piece of information I'm interested in. We do have this other stuff. We also have an x squared y and an xy squared, and on the other side, of course, 1 times 2 is 2. But let's look at those two terms that aren't a part of what we want. At this point, we want to try to do a little clever factoring. What do these two terms, x squared y and x squared y, have in common? They both have xy. What does it leave behind when we factor out that xy? Well, there's an x from this x squared here, and there's an extra y from this y squared. And so in fact, what we're looking at is x cubed plus y cubed. Again, that's the thing we're trying to solve for. That's what we're interested in. Plus xy times the quantity x plus y. And all of this is equal to 2. You will probably notice at this point, we have absolutely everything that we need. We already know what x times y is. We figured out over here, it was equal to -1/2. We also know what x plus y itself is. That's our first piece of information. That's what we labeled A. The whole thing again equals 2, and as we multiply that out, we get x cubed plus y cubed minus 1/2 equals 2, which means we can simply add 1/2 to both sides and find the piece of information we were interested in. X cubed plus y cubed equals 2.5. This leads us into our third problem-solving principle, answer the question asked. You'll notice what we've solved for here is x cubed plus y cubed, not what x and y are individually. There is an interesting way to solve for x and y individually. In fact, there's an interesting way that comes specifically from a new perspective. Imagine that I took those first two pieces of information and actually decided to think about them graphically. X plus y equals 1 is this red line here with a y-intercept and an x-intercept of +1, and x squared plus y squared equals 2 is actually the equation of a circle centered at the origin with a radius of 2. I can see that there are two different intersections between those two pieces of information. There must be two by symmetry. That is, because in the original set of equations, there was no difference between x and y, they were interchangeable for each other, our solution must have two different possibilities. In this particular case, you can distinguish them because in one case, x is positive and y is negative, and in the other case, that flips around. X is negative and y is positive. Helping people see new perspectives that illuminate mathematics in a different way is one of my great passions as a math teacher, and that's why I'm so happy to have Brilliant.org sponsoring today's video. It is an amazing platform for helping people develop the kinds of intuitions that would allow you to solve a problem like this. Brilliant.org helps you learn mathematics interactively, though that really only scratches the surface of what you can accomplish on the Brilliant platform. Brilliant has thousands of lessons available, not only on topics like foundational mathematics, but also on AI, on data science, statistics, neural networks, with more lessons added every month. One class I'm particularly eager to share with you is Brilliant's algebra courses. They've got one for Algebra 1 and for Algebra 2. You can see, for example, this great lesson on Algebra 2 for precisely what we're looking at now, taking advantage of symmetry to try to simplify problems. Brilliant's platform is built for interactivity, helping you think through the way changing different parameters affects your graphs or solutions or what have you, and then showing you in the explanation what goes wrong if you're misunderstanding something and how to get it right the next time. To try everything Brilliant has to offer free for a full 30 days, visit brilliant.org/polymathematic. I think you'll see the link over here, or click on the link in the video's description. The first 200 people to click on that link will get 20% off Brilliant's annual premium subscription. Whether you're a student going through this stuff for the first time or a lifelong learner who's tackling new skills, I think Brilliant.org's platform can help you, and I'm very thankful to them for sponsoring today's video. So back to our problem here. We've solved the easier question. We have an idea of how that's going to work. We're approaching it pretty heavily symbolically. We're multiplying stuff, we're factoring stuff, and now we just need to apply that to our original three-dimensional problem. So let's start again by labeling some of this information. I'll call the first piece of information A, that second piece of information B, third piece of information C, the fourth piece of information, what we're actually trying to solve for here, x to the fourth plus y to the fourth plus z to the fourth, I'll call that D, and then we want to see what else we can figure out to get to D. Again, I'm going to begin by taking that first piece of information and just seeing what happens if I square both sides of that equation. Now, I won't bore you with the actual actual expansion in this case, but we can see, generally speaking, on the left-hand side, we're multiplying a times a. On the right-hand side, we've got 1 times 1, which is, of course, 1. After we multiply all that out and collect our like terms, we get this. X squared plus y squared plus z squared plus 2xy plus 2xz plus 2yz all equals that same 1 because, again, we're just multiplying out something that we know equals 1 by itself. Again, like before, you can see that's going to lead us to some interesting substitution. We know that x squared plus y squared plus z squared is equal to 2. So in fact, what we can do here is replace x squared plus y squared plus z squared with 2, and then solve specifically for some new information. In this case, that's going to be that 2xy plus 2xz plus 2yz equals -1. And again, like we did on the simpler problem, we're going to divide everything by 2 to get our first new piece of information. We'll call this E. We know that xy plus xz plus yz must be equal to -1/2. You're probably sensing a theme here. We're going to move on now to multiply out a times b. So we're just going to keep trying to generate new pieces of information from the information that we already have. On the left-hand side, again, I won't bore you with the details. You can have Wolfram alpha or something like that multiply those two trinomials for you. But what we get is x cubed plus y cubed plus z cubed plus x squared y plus xy squared plus x squared z plus xz squared plus y squared z plus yz squared. And all of this is supposed to be equal to 1 times 2 equals 2. Again, we want to engage in some clever substitution now. We know what x cubed plus y cubed plus z cubed is supposed to be. It's supposed to be 3. So we can actually just replace this here with 3, and then subtracting that same 3 on both sides, we get that x squared y plus xy squared plus x squared z plus xz squared plus y squared z plus yz squared is all equal to -1. Again, similarly to what we already did on the simpler problem, I'm going to try and do some clever factoring now. In this case, I'm going to group 2 pairs of terms at a time, terms that share 2 variables in common. For these first 2, we can see that they share x and y in common, and again, after we factor, it's going to leave an x plus y behind. For these next 2, they share x and z in common, and they leave behind an x plus z, and for this third set, they share a y and z in common, and they're going to leave behind the sum y plus z. Now, x plus y is interesting because although we don't specifically see x plus y equals blank in this information that we already have, we do know, for example, that x plus y plus z is equal to 1. So we can very easily just subtract z on both sides and say that x plus y is the same thing as 1 minus z. This means that we can replace this x plus y with 1 minus z, and similarly we can also replace x plus z with 1 minus y, and y plus z with 1 minus x. This is useful because we can now multiply these terms back out, and they're going to look a little bit different than what they did before. xy times 1, of course, is xy, and then xy times minus z is minus xyz. Continuing to distribute, we get plus xz minus that same xyz, and plus yz minus, again, xyz. And we're still not doing anything on the right-hand side, so that just stays -1. Collecting together some like terms here, we're going to get xy plus xz plus yz minus 3xyz is equal to -1. And one more time, we've got some substitution that we can engage in. We know that xy plus xz plus yz is equal to -1/2, and so we can replace that whole quantity with -1/2. This is going to allow us to solve specifically for what x times y times z is equal to. Let's add the 1/2, add the 1/2, and we get this. -3xyz is equal to -1 plus 1/2 is -1/2, and dividing by -3, dividing by -3, or if you prefer multiplying by -1/3, we should get this new piece of information. X times y times z is equal to +1/6. Let's add that to our list over here. We will call that piece of information f, and we are almost done. There's just one other thing we need to do to figure out what x to the 4th plus y to the fourth plus z to the fourth equals. One more time, we want to be a little bit clever about what we multiply. This time I'm going to multiply a times c, which of course I should know is equal to 1 times 3 equals 3. Again, I won't bore you with the details, but if you multiply that out, you should get x to the fourth plus y to the fourth plus z to the fourth plus several more terms. We should have an x cubed y plus xy cubed, an x cubed z plus xz cubed, and a y cubed z plus yz cubed, and all of this equals 3. At this point, we can see the piece of information we want. We're trying to isolate x to the fourth plus y to the fourth plus z to the fourth, so let's move everything else over to the other side. This would be the same thing as saying x to the fourth plus y to the fourth plus z to the fourth equals 3 minus x cubed y minus xy cubed minus x cubed z minus xz cubed minus y cubed z minus yz cubed. We have what we want isolated on that left-hand side, so we just have to do some clever factoring to turn all those symbols into numbers. Again, I'm going to suggest let's group these different terms into sets of 2, and let's isolate the 2 variables they have in common. We can pull out a minus xy from those first 2, and it leaves x squared plus y squared. We can pull out a minus xz from the next 2, leaving x squared plus z squared. I'm running out of room here, my goodness. And we can pull a yz out of the last 2, leaving y squared plus z squared. Just like before, we want to be clever about our substitution. We can see, for example, that x squared plus y squared should be the same thing as 2 minus z squared. And similarly, x squared plus z squared is 2 minus y squared, and y squared plus z squared is 2 minus x squared. And again, like before, we're now going to multiply that back out. So we're going to basically undo the factoring we just did, but it's going to give us new, more useful expressions. 3 minus 2xy plus xyz squared minus 2xz plus xy squared z and minus 2yz plus x squared yz. Again, as we are doing all of this distribution. You can see I've grouped them such that we can take advantage of that xy plus xz plus yz piece of information we've used several times now, and so we can do a bit of clever factoring with these 3 variable terms, xyz squared, xy squared z, and x squared yz. I may have said one of those twice. I don't know. Let's actually go ahead and rewrite that 3 minus, and I'm going to go ahead and factor that minus 2 out of those terms, leaving behind xy, xz, and yz. And similarly, let's go ahead and factor out the 3 variables that those 3 terms have in common, plus xyz times x plus y plus z. And that's basically it. The 3 stays 3, the minus 2 stays minus 2, but that xy plus xz plus yz we know is equal to negative 1/2. That xyz we know from the work that we did before is the same thing as 1/6. And of course, from way back at the beginning over here, we know that x plus y plus z is equal to 1. And so finally, what is x to the fourth plus y to the fourth plus z to the fourth? 3 plus 1, negative 2 times negative 1/2 is positive 1, plus 1/6, 1/6 times 1 is 1, and 3 plus 1 plus 1/6 is the same thing as 4 and 1/6. And that's it. That is the answer to our problem. Going back to our principles, I hope you can see how it was helpful to solve an easier problem first, how at almost every step in the process we had more information than we thought we did, how you'll notice we still haven't even solved for x, y, and z. It is possible to do so, but in this case it would be really helpful to have a new perspective on it. I leave it as an exercise to the viewer. If you could graph this 3-dimensionally, you would have the equation of a line in 3 dimensions, the equation of a sphere in 3 dimensions, and then the equation of this weird kind of tabletop in 3 dimensions. The 6 intersections between those 3 graphs, 6 because, again, we know x, y, and z must be essentially the same as each other by symmetry, and so the number of ordered triples that would be our solution, there must be 3 factorial way to organize them. There must be 6 different ways to organize those. Those 6 different ordered triples would appear as the intersection of those 3 graphs in 3 dimensions. Thank you again to Brilliant.org for sponsoring today's video. I strongly recommend you check out that link one more time, brilliant.org/polymathematic. The first 200 of you to take advantage of that will get 20% off Brilliant's entire annual premium subscription. That's a great deal for anyone interested in growing in mathematics. Otherwise, I will see y'all next time.